بسم الله الرحمن الرحيم. بنرحب فيكم في محاضرة رقم 15 في الإجراءات إشارية رقمية Digital Signal Processing. اليوم رح نتكلم عن Discrete Fourier Transform Theorems. Theorems. اوكي، حتى نبدأ في دراسة الثيورمز اللي بتخص ال DFT خلينا ناخذ two sequences G of n إلها DFT pair G of k and H of n إلها ال Fourier transform H of k. So you have those two sequences وبناء عليهم راح نشوف الثيورمز احنا وياكم مع بعض. The first one, the first theorem is linearity. Linearity theorem. وهنا نقدر نقول انه في we have a linear combination of G of n and H of n. So you have a linear combination of both. You will have exactly the same linear combination in their frequency transform. Alpha G of k plus beta H of k. Okay? So this is linearity and it applies because of the definition of the Fourier transform. The second theorem is circular time shifting. Theorem. And you have, if you have a circular shift in time domain, so you have a circular shift G of n minus n0 modulo n. It has the DFT of G of k, but with a phase shift. So you have a phase shift with W sub n to the power k n0 G of k. You can notice that phase shift in time domain, you have a phase shift in frequency. Okay? The magnitude of W sub n is always 1. So the magnitude of G of k does not be affected. It's not be affected by the circular time shifting. But you have a phase shift added to the frequency domain transform. Okay. 3. Circular frequency shifting theorem. And here it will be phase shift in time domain, W sub n to the minus k0 n. G of n has the DFT pair of the shift in frequency, k minus k0 modulo n. So shift in frequency, phase shift in time, shift in time, phase shift in frequency. Okay? And this is something that I think most of you know that from signals and systems. Okay, the fourth theorem, or sorry, the 1, 2, 3, 4 theorem is the duality theorem. And the duality theorem says that if you have some G, notice that you have G capital, but of N, it has the DFT of N, but with G small of minus K modulo N. So this is a duality theorem. I think this is something very similar to the what you have learned in signals and systems. If you remember, we said that if you have a rect, then its transform is a sinc. But if you have a sinc, its transform is a rect. So those are dual of each other. Now, let's take an example here to see how the duality theorem works. Notice that this function, this is in time, although we said that G capital of K is frequency. Now, if we have some time domain sequence that looks like exactly the same as G of K, which is in frequency, and we need to transform it into frequency domain. How it looks like? It looks like some form of the G small of it. I will do this through the following example. We know already from previous examples that if you have G of N, which is equal to 1, 2, 0, and 1, we did its DFT, and we find the DFT of this sequence to be 4, 1 minus J, minus 2, and 1 plus J. So this is our G of N, and this is our G of K. Okay? Now, what the duality theorem said, if you take this one here, the G of K, and you assume it as if it is a time domain sequence. Now, I'm going to look at this. What will be if you have this in time domain? 4, 1 minus J, minus 2, 1 plus J. And I need to find its DFT. See? So this was a previous example. I put it here just to demonstrate the idea. Now the idea is I'm going to take this G of K and I'm going to assume that it is a time domain sequence. Right. What will be the frequency domain? It should be something like this. It should be 4, because N is equal to 4. G small, which is, but with a minus K modulo N, modulo 4. Okay? So this is supposed to be the DFT. We can do this by multiplication with D4 and find the answer, but we're going to do it first with comparing G and a flipped G, or time inverted G. What will be the time inverted G? It will be 4 times the sequence G, but to be inverted. Now, the inversion of minus K modulo 4 for this G of N here. The first element is the same. G of 0 modulo 4, it is the same as 1. Now the others, they will be flipped. So this one will be 1, which is this one, then 0, and the last one will be 2. So G of minus K modulo 4, you take this one and you do the flipping of this, and you get this answer, and it will be 4, 4, 0, and 8. So this is our DFT of the sequence 4, 1 minus J, minus 2, 1 plus J. Okay? So this sequence has the Fourier transform, and we did it through the duality theorem. We took G of N, we flip it with the circular time reversal, and we multiply it by N, and we get the answer. Let me just make sure that this is the true answer by doing the Fourier transform of the sequence itself, and show you that Okay, I'm gonna show you, check our answer by multiplication 1, 1, 1, and 1, 1 minus j minus 1j, 1 minus 1, 1 minus 1, 1 j minus 1 minus j. This is d4, so this is our d4, and we will multiply this by our x, which is 4, 1 minus j, minus 2, 1 plus j. And if we apply this, you will get from the first one, it's 4 plus 1 minus j minus 2 plus 1 plus j. So this is the first element. The second element is 4 minus j minus 1 plus 2 plus j minus 1. The third one is you multiply the third row by the column, and you have 4 minus 1 plus j minus 2 minus 1 minus j. And the last one is 4 plus j plus 1 plus 2 minus j plus 1. And you have plus j minus j, 4 plus 1 minus 2 plus 1. So this is equals to 4. The second one is also 4 minus j plus j minus 1 plus 2 minus 1. So this is also 4. The third one is minus 1 minus 2 minus 1 minus 4 plus 4 is 0. And the last one, you have 4 plus 1, 5, and plus 2, 7, plus 1, 8. So this is the answer. So it's the same answer that we got through the duality theorem, and our check is okay. So this is good. Okay. Okay, so enough with the duality theorem. Let's go to a very important theorem here, which is the convolution theorem. And the convolution theorem says that if you have a convolution or circular convolution in time, then you have multiplication in frequency. So number 5 is the circular convolution. Circular convolution. So G of n, circular n with h of n, it has the DFT of G of k times h of k. Okay? And this is one way to do the circular convolution. You can make use of it in a way such that you can change or you can transform G of n into frequency domain, h of n in frequency domain, do the multiplication and do the inverse, and then you get the resultant of the circular convolution. Why do we do that? It's usually easier to do it in computers. When you do computer algorithms or you do simulations in computers, it's easier to do that in frequency rather than doing that in time domain. Okay? And we can show that in a block diagram form. If you have endpoint DFT, and you have another here block with endpoint DFT, and you apply here x of n, okay, with length n, and you have here h of n with length n, then you got here, G. So you have G of k here, and you get here h of k. You have to multiply both of them and get the answer as y of k. And here you have a endpoint inverse DFT, And you get the answer here as yc of n, length n also. Okay, so this is a block diagram showing how can we implement the circular convolution in time domain using the DFT theorem for circular convolution, multiplication in frequency. So this is the circular convolution. Circular convolution using the DFT. Okay, circular convolution using the DFT. I will demonstrate this by doing the example that we did before last time when we did the circular convolution. So our example is, again, we have g of n equals to 1, 2, 0, and 1. H of n equals to 2, 2, 0, 2, 2, 1, 1, sorry, 1, 1, and compute the circular convolution using DFT. So we need to compute yc of n, which is the convolution of those two. So to do this, we're going to do what we have here in the block diagram. We first need to find g of k, which is equal to g as a vector. So g as a vector equals d4 times g as a vector. So this is equals to 1, 1, 1, 1, 1 minus j minus 1j, 1 minus 1, 1 minus 1, 1 plus j minus 1 minus j times 1, 2, 0, and 1. And the result of this, we already have it. It is equal to 4, 1 minus j minus 2, 1 plus j. So this is the answer of the first one. And we have also h equals to d4 times h. And it's the same. 1, 1, 1, 1, 1 minus j minus 1j, 1 minus 1, 1 minus 1, 1 j minus 1 minus j times the second sequence, which is 2, 2, 1, and 1. And the answer here is 6. 1 minus j, 0, 1 plus j. Okay? So next step is to multiply g of k. So our y sub c of k is equal to the multiplication of, let me put it in form first. Let's say that this is equals to g of k times h of k. So this is equals to 4, 1 minus j minus 2, 1 plus j. And you have here point by point multiplication. It's a point by point multiplication. So y of 0, yc of 0, it's g of 0 times h of 0. So you multiply the first element with the first, second with the second, third with third, fourth with the fourth, with the fourth one. So this is 6, 1 minus j, 0, 1 plus j. And so the result is 24. 4 times 6, 1 minus j squared. It's equal to minus j2, 0, n plus j2. Okay? So this is yc. Now, to get yc of n is equal to 1/4 d for complex conjugate, which is 1/4 d complex conjugate. D fourth complex conjugate is the inverse of d4 times yc of k. Okay, so you'll have 1/4 times the complex conjugate of this matrix is the same 1, 1, 1. They are real. 1, the complex of minus j is j, minus 1 is the same. J is minus j, 1 minus 1, 1 minus 1. Those are real values. And here is 1 minus j, minus 1, and plus j. So if you multiply this by y sub c, it's 24 minus 2 minus j2, 0 plus j2. So we will have the answer to be, first one is 24 divided by 4. So this is equals to 6, 7, 6, and 5. Okay? Which is the same answer that we got when we did the convolution. If you remember, we did the convolution. Just let you do it in a very fast way. The circular convolution, we did it last time. We have 1, 2, 0, and 1, 2, 2, 1, and 1. And we multiply 2, 4, 0, 2. And then we have space, then also 2, 4, 0, and 2. And 2 spaces, 1, 2, 0, and 1. And the last one is also 1, 2, 0, and 1. But before we add, we took those 2, 0, and 2, and we cancel those. And we take 1 and 0, and we cancel this, and we take this 1 to be here, and we cancel. So we add those, 2 plus 2 plus 2, this is 6. 4 plus 2 plus 1, this is 7. 6, and the last one is 5. And this is our yc of n. And this is also to say equals to yc of n. So yc of n is 6, 7, 6, and 5 by the tabular method and by the convolution theorem of the DFT. Okay? Okay, so let's move to the next theorem. The next theorem says it's the dual of the convolution, which is the modulation or the multiplication. So number 6 is the modulation theorem. Modulation theorem says that if you have g of n times h of n in time domain, then it has convolution in frequency, and it has the form 1 over n summation from L equals 0 up to n minus 1 g of L times h of k minus L modulo n. So convolution, this is a convolution sum, but scaled with 1 over n. So you will have the frequency domain, the time domain, and this is the modulation theorem. Okay, number 7 is the Parsevals relation. And as I mentioned before, the Parsevals relation is a relation between, for signals, the energy of the signal. Actually, it's a relation for the energy of the signal. You can find the energy of the signal in time domain or in frequency domain. It doesn't matter. It should be exactly the same amount of energy. If you look at the signal from time domain perspective or from frequency domain perspectives, it shouldn't matter. The energy is the energy. It has a certain amount of energy, and you need to calculate this energy. It differs in the how to calculate it, but at the end, it's the same amount of energy. So if you look at it in frequency domain, you have an amount of energy. And if you look at it in time domain, you have exactly the same amount of energy. And it should be the same in both. Okay, Parsevals relation says that if you have an inner product between two sequences, g of n times h complex conjugate of n, from n equals 0 up to n minus 1, this is equals to 1 over n times the summation from k equals 0 up to n minus 1, g of k times h complex conjugate of k. So this is the inner product in time domain of two sequences. This is the inner product of time domain in frequency domain of the two sequences, normalized by 1 over n. Notice here that, please be careful, that Parsevals relation is not a Fourier transform pair anymore. It's equality. This is equal. So you can find this. This is a formula, and the end result is a number. So it's a number of energy. Inner product is a scalar quantity. So this is a scalar quantity. This is a scalar quantity. This is a sequence here. This is a sequence. So you have a sequence, you have a sequence. G of n times h of n equals some y of n, which is the modulation, the multiplication of those two sequences. But here, this is the inner product of, if you think of vectors, the inner product of vectors is a scalar quantity. And this is the same. Now, if we take, if g of n is equal to h of n, so if g of n equals to h of n, then this summation will be the amount of energy in the sequence, which should equal 1 over n summation from k equals 0 up to n minus 1 magnitude of g of k squared. Okay, so you can find the energy of the sequence in time domain. You have the alternative to find the energy of the sequence in frequency domain. Let's see an example doing the energy in both in time domain and frequency domain. Okay, so if we have an example, g of n equals to 1, 2, 0, and 1, and we know already that g of k is equals to 4, 1 minus j, minus 2, and 1 plus j. Okay, I'm gonna find the energy of the signal, the sequence. Find the energy of the sequence. We know that the energy of the sequence is equal, okay, E sub g is equal to the summation g of n magnitude squared from n equals 0 to 3, and this is equals to 1 squared plus 2 squared plus 1 squared, and this is equals to 6. So you have 6 units of energy. We also can find E sub g is equal to 1 over 4. You have 4 elements, summation from k equals 0 to 3, magnitude of g of k squared. And this is equals to 1/4 times. The first one is 4, so it's 4 squared. It's real value. The second one is complex. Please be careful that this one is not 1 minus j squared. This is the magnitude squared. This is a complex quantity. The magnitude squared is the real squared plus the imaginary squared, but without using the square root. So this is equals to 1 squared plus minus 1 squared. The real squared plus the imaginary squared. plus minus 2 squared, and the last one is plus 1 squared plus j, which is the magnitude of j is 1 squared, and we close it. So you have 1/4 times 16 plus 1 plus 1 plus 4 plus 1 plus 1. So you have 24 over 4, and this is equals to 6. So you have 6 units of energy. You have 6 units of energy. This is in time domain, this is in frequency domain, and this is what the Parsevals relation is all about. It's about finding the energy, or it's actually the general rule of the Parsevals relation is the inner product of 2 sequences in time domain and in frequency domain. And if you use the inner product with the sequence itself, with itself, the inner product of the sequence with itself, then you have the energy of the sequence, which can be found in time domain and in frequency domain, and it should give us exactly the same answer. Okay. So with this, we end up our lecture about theorems for the DFT. We still have some small topics about the DFT, but we will postpone it for the next lecture. Thank you for being with me, and I will see you in next lecture. Thanks.